Imagine being able to peek behind the curtain of reality, not through science fiction, but through actual experiments in real-world laboratories. For over a century, scientists have been fascinated by something called the observer effect, the strange idea that simply watching a quantum particle can change its behavior. This isn't just a weird theory, it's backed by real experimental data that has puzzled physicists since the early 1900s. But now, something extraordinary has taken place. Google's quantum core has shaken the foundation of this mystery. In just 5 nanoseconds, researchers were able to observe and predict particle behavior with unprecedented accuracy. This was done using Google's advanced quantum processor, not just a regular computer chip. The results were so clear and controlled that the mystery of observation affecting outcomes began to unravel. Traditionally, trying to observe a quantum particle would collapse its wave function, essentially ruining the state scientists were trying to study. But Google's quantum team took a new approach. They used entanglement-based probes to examine particles in motion, without collapsing them, while simultaneously predicting their behavior. This was not just a measurement, it was a real-time conversation with particles, and it changed everything. The experiment used a superconducting chip cooled to temperatures near absolute zero. This extreme cold environment was necessary to allow fragile quantum simulations to run without interference. In earlier attempts by physicists, such as those in the 20th century, any observation would distort or destroy the quantum state. But now, the observation became part of the experiment itself, creating a seamless loop between observer and observed. This approach flips the observer effect on its head. Instead of being a philosophical obstacle, it's now a scientific tool. We can now guide quantum particles instead of disturbing them. This opens the door to building more stable and accurate quantum computers, potentially free of many errors that previously made them impractical. The roots of this idea go back to 1927, when Werner Heisenberg introduced the uncertainty principle. He said that the more precisely you know a particle's position, the less you know about its momentum, and vice versa. That concept still holds true. But it no longer means we must sacrifice precision in every measurement. Back in the 1980s, early quantum computing researchers had a dream. What if we could use the act of observation as part of computation? At the time, it was just a dream because the technology didn't exist. That changed with Google's quantum chip, a processor that took 5 years to develop and was capable of running what's called real-time feedback loops. These loops allowed the chip to not just record what was happening, but to react as it observed. Imagine not taking a photograph of a moving particle but having a conversation with it, asking questions and responding instantly. This is what's known as active measurement, and it's one of the most groundbreaking shifts in how we understand the quantum world. From this, a new theory began to emerge. What if observation is not a barrier but a bridge? What if measurement and evolution are actually the same event, experienced from different angles? Using Google's chip, we're not just watching particles settle into a state, we're helping guide them there in real time. That kind of guidance could transform how quantum systems operate. Imagine quantum computers that fix their own mistakes before they even happen, or quantum sensors that adjust mid-measurement for extreme precision. These aren't ideas from the future, they're being tested now. The implications go even deeper. If we're influencing quantum particles just by observing them, who or what is really doing the observing? Does this bring consciousness into the equation? Some scientists wonder whether the universe reacts not just to measurement, but to the presence of an observer, a notion once felt too strange to be true. In one groundbreaking test, scientists at Google found something they didn't expect. Particles that were watched for longer periods began to exhibit a kind of memory. This phenomenon, dubbed self-referential coherence, showed that particles under observation became more stable in certain quantum states the longer they were observed. At first, the team suspected a hardware glitch. But after dozens of trials, the pattern remained. Something real was happening. Dr. Anna Kao from MIT said, "This could represent a new kind of physical law, one that only appears under continuous observation." Another physicist, Dr. Eric Lindstrom from Caltech, added, "It's like the quantum system is adapting to us. Could we be seeing new layers of physics, hidden in plain sight?" The scientific community began to split, some intrigued, others skeptical. The skeptics suggested this might be a fluke of engineering, not a new principle of nature. To test this, Google's team replicated the experiments using completely different systems like trapped ions and photonic qubits. Surprisingly, these systems showed even stronger feedback behaviors. That meant it wasn't just about the chip, it was about the underlying physics. But Google didn't stop there. They combined their quantum computing platform with a deep learning AI. A neural network was trained on large datasets of quantum particle behavior, learning how qubits reacted under various conditions. During experiments, real-time data from the quantum core was fed back into the AI, allowing it to adjust its understanding on the fly. This AI wasn't just getting better at predicting, it began to rewrite its own logic, discovering strategies no human had imagined. According to Dr. Alina Zhou from Stanford, we watched an AI co-evolve with the quantum system. That's not prediction, it's partnership. The AI was learning alongside the processor, developing something physicists called quantum intuition. Traditional AI relies on existing data, but this system was learning from first principles, seeing new patterns that humans would never recognize. This kind of learning could revolutionize industries, from drug discovery to climate modeling. Imagine pharmaceutical companies using subsystems to discover entirely new molecules, or weather models that adapt in real time as conditions change. This goes beyond computing. It becomes autonomous discovery, a way to explore the universe that doesn't rely entirely on human guidance. But this also raises profound ethical questions. If AI can evolve alongside quantum processes, what role is left for humans? Our position is changing. We are no longer just engineers tweaking machines. We're becoming designers of learning environments, guiding AI's goals, interpreting its results, and ensuring it acts responsibly. According to Dr. Evelyn Harper, an ethicist, we're building minds we don't fully understand. We must be careful with what we empower them to do. At the same time, these systems could democratize science, giving small labs access to the kind of computing power only tech giants had before. This new partnership between human and machine could help us explore the most unanswerable questions, like the nature of dark matter, the origin of consciousness, or designing eco-friendly materials to fight climate change. At the heart of this revolution lies the transformation of the observer effect. Once viewed as a problem, it's now a solution. The line between watching and interacting is vanishing. The particle and the probe are no longer separate. They're partners in a quantum dance. Dr. Koichi Tanaka from Tokyo University called this the birth of interactive physics. We're not just looking anymore, we're in the experiment, we're shaping it with every interaction. This kind of feedback, where the system corrects itself before an error occurs, could lead to the first millions of stable qubits, the cornerstone of true quantum computing. These new quantum AI systems might even design their own experiments or propose theories far beyond current human understanding. They could explore quantum realms too vast for traditional logic, uncovering new laws of nature simply by interacting with the data. The consequences for humanity are monumental. From revolutionizing medicine to building self-optimizing energy grids, the potential is staggering. But we must also ensure that such power is used wisely and ethically. Transparency, regulation, and oversight are more important than ever. So where do we stand today? Google's quantum experiment has not just cracked a physics puzzle. It has redefined reality itself. We are no longer passive observers, we are now participants in the quantum story. The universe is not just something we study, it is something we help shape. If you've made it this far, you're already part of a new community, one that dares to ask bold questions. What does this mean for consciousness, for science, for the future of knowledge? Subscribe to our channel and thanks for watching.